So group 1 was focusing on the difference between logistic regression models based on Bernoulli and binomial data. So the group members are Abigail, myself, Parfait, John Andrew, Pauline, and Nevin. I'll start with the introduction, just a brief overview of logistic regression. We know that logistic regression is used when the dependent variable is a binary. That means it has two outcomes. It can be 0, 1, no, yes, success, failure. And the dependent variables, these are the predictors, can either be continuous or categorical. And the logistic regression is used to model and predict the probability of a binary outcome. And we normally use the generalized linear model, and in R, we use the GLM function. So the purpose of our presentation is to compare Bernoulli and binomial data in logistic regression. For this presentation, we used an inbuilt data in R called the INFAT. This is a data set that is from a retrospective study that was conducted by CDC, that is the Center for Disease Control in the US, to check on the factors predicting the infertility of women or in women. And these are the factors associated with infertility. And it was a case control study. So the key variables in our data set, there is the case, this is our outcome, which is either infertile or fertile, education, age, parity, induced abortion, spontaneous abortion, all these are predictor variables. And you'll notice that education, induced abortions, and spontaneous abortions are factor variables. And then we have age, as age and parity as numeric variables. So I'll start with using the data to model for a Bernoulli output. So understanding of Bernoulli data, we say it's a variable. A variable is said to have a Bernoulli distribution, which is binary, with values representing success and failure. And each observation represents a single trial with a binary output. So in short, for Bernoulli data, is when you do an experiment, and in that experiment, you only have two possible outcomes, and you do the experiment only once. So at the end of my presentation, we are going to look at the data set having been modeled using a Bernoulli model. Then when we modeled the data, this was our output. So we were predicting the dependent variable was case, this was the outcome, and the independent variables or the predictors were education, age, parity, spontaneous abortions, and induced abortion. So maybe I'm going to explain what this means. Spontaneous abortions, according to this data, is the natural loss of pregnancy, and then induced is intentional termination of a pregnancy. So from our output, we got the odd ratios, the confidence intervals, and the p-value. And when you look at this table, the main predictors are those which have a p-value of less than 0.05. So if you look at it, the main predictors are spontaneous abortions and induced abortions, because education, age, and education and age have a p-value that is greater than 0.05, but the rest, that is parity, spontaneous abortions, and induced, all have a p-value less than 0.05. So they are main predictors of our outcome, which is whether you're fertile or infertile. So that was the output of Bernoulli data. And then we go to binomial. We are going to discuss this output later on and what it means. So for binomial data, it counts the number of successes out of a number of n trials. So you do an experiment which has two outcomes, but you repeat it n times. And in binomial, there are ways of achieving a binomial distributed data. There are three. The first one is grouped data from the onset. So when you go to the field, you're collecting grouped data. For example, collecting number of vaccinated individuals from different clinics. So the rows will have the different clinics, maybe clinic A and clinic B. And in clinic A, you get maybe 50 out of 100 are vaccinated. And in clinic B, you get maybe 40 out of 120. So that is, you're collecting the data, grouped data from the onset. Then you can have a binomial distributed data by repeated binary outcomes. This is where an experiment or a trial is repeated for the same individual several times and the number of successes recorded. And I think we've had this example in class where we have 3 biostatistics cards. And then we monitor the performance of each individual with a score greater than 20 out of 30, taken as success, and below that as failure. And then we count the number of successes in the 3 cards for each individual. Then we have the Bernoulli trials aggregated later. This is where an experiment is performed once on a participant, then the data is later aggregated based on the investigator's interest. So for example, n women with the same demographics are grouped, then the number of women who exhibit the outcome of interest are recorded. So this is why you collect individual data, but during analysis, you group them together depending on your outcome of interest. And in our analysis, we focus, it's more of option 3, where we have Bernoulli trials aggregated during analysis, because we used the same data set for Bernoulli and then we aggregated it to use it for binomial modeling. So when you modeled using binomial, we grouped the factors together, that is education, age, parity, induced and spontaneous abortions, and then we were calculating the successes, which is some of the cases of infertility, and the failures as the trials minus the successes. And then, so the dependent variable was, you combine both successes and failures, and then the independent variables, the predictors were education, age, parity, spontaneous and induced abortions. And from this output, you've noticed it's the same as the one of Bernoulli. So there is no much difference. And then to interpret our results, so when you look, we said that the main predictors, depending on the value of the p-value, is parity, spontaneous, and induced abortions. When you look at parity, you see an odd ratio of 0.44. So maybe just to mention that when you run the model, GLM, the output is the log odds. So you exponentiate them to get the odd ratios, which then we are using for our interpretation. So it means that each additional prior pregnancy reduces the odds of infertility. So 0.44, meaning that from our definition, parity is the number of pregnancies you've had before. So if you have, depending on the number of children you have, which determines maybe the number of pregnancies you've had before, if you have many children, then you're less likely to be infertile. That's the interpretation. Then when you go to spontaneous, one spontaneous abortion increases the odds of infertility by 7.62 times. Remember, I said that spontaneous abortions it's the natural loss of a pregnancy or a miscarriage. So meaning that if you have, the more miscarriages you have, the more likely you are to be infertile, because it means maybe there is an underlying health issue that is affecting your fertility. So meaning that one spontaneous abortion increases the odds of infertility by 7.62 times, and then 2 or more increases the odds by 60.3. Can see when the factor is 1, it's 7.62, and then when it's 2, 60.3. And then the other one is induced, which when the factor is 1, it's 3.52, and 2 or more, 13.4, meaning that one induced abortion increases the odds of infertility by 3.52 times, and then 2 or more increases the odds by 13.4 times. So the more you're carrying out induced abortions, the more you are increasing your likelihood of being infertile. So, and as you've noticed, these interpretations hold for both Bernoulli and binomial models. And this is due to their equivalence in this context. So, as you've seen from our results, the odds ratios, the confidence intervals, and the p-values are identical. So the reason is the likelihoods of the two models are equivalent when the data are structured appropriately. So remember, these two have the same link functions. That's the logit. So that's why their outputs or the results are the same. So what does this imply? That if you are choosing between Bernoulli and binomial models, that depends on your data collection methods. Are you intending to collect group data or individual data? And also the nature of the research question, because you can also collect individual data, but group it during analysis depending on your research question. So that's the main difference, or the criteria to use when you're selecting between Bernoulli and binomial models. And then these are the R codes for Bernoulli. You can see, and then for binomial. So their structure is a bit different. Okay, that's all.
Thank you, Consolata. We can clap for her for the wonderful presentation. Any questions, any contributions to whatever presentation she's made is open. Just raise your hand or go ahead and ask a question or add. Yes, Prof, go ahead.
Thank you, Consolata, for the presentation. I think it was spot on. Just a quick question. For example, there's something we usually call the dose response modeling. Dose response modeling, where, for example, you spray cockroaches. You want to know what level of dose will be able to kill cockroaches in the house. And you spray different doses to different sets of cockroaches. So you have, let's say, 20 cockroaches here, you spray, then you count how many of them die, how many do not die, or how many out of the total number die. Is that okay? At a certain dose level. Then you increase the dose to another level. Then again, you take another set, you spray, you check. So you keep on increasing the dose level. That's what we usually call the dose response modeling. Is that okay?
Yes.
Is that okay?
Yes.
Now, for that case where you are spraying the cockroaches and you are counting the number that die, which logistic regression would you do? Will you do the based on Bernoulli or based on binomial? And why?
Yeah. Is this question directed to the group or to the class?
To the group, to the group.
Okay, group members, please go ahead.
I would go for a binomial distribution because at each level, you're looking for the number that die, and then you repeat the same. So you're looking at grouped data.
100% correct. Yes, that will be grouped data. Then maybe you touch again. Maybe you can just, you've already presented it and it was clear, but just for purposes of everyone, just be sure that we are all on the same page. What is the response variable, or rather, okay, you can think of it from R perspective. In R, what is the response variable when you are doing logistic regression based on Bernoulli data? And what is the response variable in R when you are doing logistic regression based on binomial data?
Yeah, maybe I can jump in because I'm also part of group one. When doing in R, when modeling Bernoulli, the response variable is binary. Yes, no. We're interested in probability of success, binary. But in binomial, it is not binary. It is the number of successes. You're interested in the number of successes. And if we look at the model in the binomial distribution, maybe you can go to the binomial model, Consolata. Yeah, if we look at the model in the y where the y should sit, we have C-bind successes and failures. Basically, when you're fitting a binomial model with group data, R expects a two-column matrix response, which is whatever we've seen here, success and failures, and we have a two-column matrix response.
100% correct. So for Bernoulli, it's a single vector with 1, 0, 1, 0, 1, 0. For binomial, it's a matrix with the two columns, and the two columns must be, the first column must be successes, the second column must be failures. I think that's all from my side. I think it was a good work. Any question from the other members, you can proceed. That's all from my side.
Yeah, thank you.
Abigail, you can ask if the other members have questions.
Yeah, members, you don't have any questions? The class? If there isn't any question, I think I had one. Or as we wait for someone else, they have a question. I came across conditional relationship or conditional logistic regression, and I was wondering what it is in the context of what we are discussing.
So conditional, it means that you are conditioning it on another variable. For example, if you are doing spatial analysis, especially, it's a common model there where you are modeling the response variable conditioned on observations that are nearby. So
Okay.
it's something along those lines.
All right.
Yeah. So it means that when your response variable will be y given something else, y given something less. If it is spatial, then it will be y at location I given y at another location. That's what we call conditional logistic.
Okay.
Yeah.
Thank you. Any other question from the class? If there's none, let's appreciate group one as we move to the next group, group two. You are looking at.
Thank you. That was a good presentation. Thanks.
Yeah, thanks. Yeah, group two members, please go ahead and share.
Hi, good evening, everyone.
Good evening.
For group two, we were tasked to do a presentation on nominal and ordinal regression. we will first do a presentation, an overview of the nominal and ordinal regression. And after that, we will go straight to R and try and see how we can do the model fitting of the two. So I'll ask Jen if she can proceed and do the presentation, and then she'll invite the next member to continue the presentation. Over to you, Jen.
Hello, good evening. I hope you can hear me. Are you able to see
Yes.
my screen?
Yes, we can see your screen.
Let me move it a bit. So for group 2, we were looking at the nominal and you are differentiating the nominal and ordinal regression and the application part of it. So me and Ian, we are doing the theory part of it, and then the other members will be doing the implementation part of it. That is the part one. So we start with an introduction. So for nominal and ordinal regression is just extension of the logistic regression, whereby the outcomes are more than 2 categories. That is, it's not binary. So we have 2 approaches, whereby the first one is multinomial logistic regression. In this case, there is no assumption on relationship between the categories. In that case, we have nominal outcomes. And then for ordinal logistic model, or it is also called the proportional odds model. It's whereby the categories are ordered, and therefore we come up with ordinal outcomes. So we have a notation whereby let y be a random variable, and then we have k discrete values. So we have k classes, 1 to k classes. Then pi subscript I2 will present the probability of the ith individual outcome belonging to the second class. So generally, if we have pi subscript ik, with the probability that the ith individual outcome belongs to the kth class. So we start with the multinomial logistic regression, which is the generalization of the logistic regression when we have more than 2 outcome categories. So in this case, the model, we start by picking a reference category. Let's say k is equals to 1. And then you model the logs odd of each of the other categories compared to the reference using this formula here. So you resolve to k minus 1 vectors of regression coefficients. And the sum of the probabilities should be equal to 1. So the probabilities and odds ratio. So the fitted class probabilities for an observation with explanatory variable vector x are given by this. So this pi1 is the probability of the reference class. In this case, it's normalized such that it's normalized based on the probability of the other classes. And for pi k is the estimated probability that the observed belongs to class k. And then we can exponentiate the odds ratios, where it's given by OR, like for this simple case here, OR KL is equals to exponential delta J beta KJ. So this is the odds ratio between the ratio of probability. Like you are exponentiating the coefficients in this case. And now the interpretation is here. Let's say we have increased the observation KJ by delta J. So in our case, we have let delta J to be equal to 1. So a 1 unit increase in predictor XJ increases the odd ratio of being in category K. So if beta Kj is greater than 1, then the odds increase with Xj. If beta Kj is less than 0, then it decreases by with Kj. So this is just the general case when we are comparing two categories where one is not a reference category. So the odds ratio are given by this formula. And the interpretation is a 1 unit increase in predictor Xj multiplies the odds of being in category K versus category L by a factor of exponential beta Kj minus beta Ij, holding all the other predictors constant. And then Ian can take over from ordinal logistic regression.
Okay, just me kindly.
Okay.
So ordinal logistic regression, let the random variable y be an ordinal response variable with ordered categories. For example, we can have poor, fair, good, and excellent. The cumulative logic model is defined as the log odds of the outcome variable y being in category J or below versus being in a higher category, given the predictor variables x is the same as the threshold for category J and the linear combination of the predictors. So as defined below, the theta J is the threshold separating the categories, J is the higher categories. Beta is a vector of regression coefficient assumed to be the same across all J. This is the proportional odds assumption. So we can eliminate the log by exponentiating both sides, and we get the equation above where we have removed the log from each side. We have introduced the exponential. Each side we remove the log. So for a 1 unit increase in predictor variable, the odds ratio for the predictor variable is in a regression model is equal to the coefficient for the XR, meaning a 1 unit increase in predictor multiplies the odds of being in category less or equal to J versus greater than J by the exponential BR, assuming all other covariates are held constant. This interpretation holds for all thresholds J. Why is it called proportional odds? Because the log odds of being in category less or equal to J versus greater than J has the same slope beta for all J. As given below, this implies that the odds change by the same factor proportional odds across the cumulative splits of the response variable. So applications for both the nominal logistic regression and ordinal logistic regression. First, for the nominal logistic regression, for example, in marketing, predicting preferred products A, B, or C. In medical diagnosis, classifying different diseases. Transportation, choice of travel mode, walk, bus, car, bike. Political science, voting for different parties. Example of ordinal logistic regression, social sciences, modeling satisfaction, low, medium, high, education, predicting student performance levels, fail, pass, merit, distinction, healthcare, disease severity ratings, and in economics, income categories, low, middle, and high. That's our first presentation. I'd like to hand over to the next group member.
Yes. Are you still presenting or you're done?
Yeah.
Abigail, I think he's done.
Yeah, they're waiting for the next group member to present.
Oh, there's somebody else
Ian,
going
who
to
is
share screen.
presenting.
Okay. Okay, so.
Hello. There's the Stephen. He will present next.
Please go ahead and present.
Yeah, so I'm going to present a multinomial logistic regression in R. Basically, I'm going to present a data set whereby we use the multinomial logistic regression to model using this data.
Joseph, are you presenting?
Yes. Are you seeing my screen?
Abigail.
Yes. This is Stephen. Who is supposed to present your R? Joseph or who?
I think Joseph was to start, and then I was to do some other part of R. So
Okay, please
let's be
do
patient.
so.
Maybe he's trying to fix something on his computer. So maybe
Okay.
we be a little bit patient to allow him to do the presentation, please.
All right.
My screen visible.
Or maybe I can present what I have as we wait for him to fix whatever he's fixing. Is it okay, Abigail?
Yeah, but he's presented. He's shared his screen. I don't know if you, Joseph. Can you hear us? Are you ready to present?
Yes. Can you hear me?
Hello.
Can you hear me?
I think Stephen. Then you can go ahead and.
Hello. Can you hear me?
Yes.
Joseph, maybe you can stop presenting.
Am I audible? Sorry.
Yes, we can hear you.
Yes.
Sorry, it's my connection, and I don't know. Are you able to see my screen?
Yes, we can see your screen, Joseph.
The screen with R code is the one visible. Kindly confirm.
Yes.
Okay, great. Sorry for that mishap. I'm going to present.
Recording stopped.
I'm going to present a multinomial regression in R. And basically, as you can see, first we need to load the libraries we will need. One is nnet. Basically, this is the one used for multinomial function modeling. The second one is ggplot. If you need to visualize your results, you need to load this library. And then the third one is the reshape library. Basically, I've written comments in this code, which I'll share with everyone so that you can be able to duplicate on your end to be able to see what's happening throughout the dataset. For this presentation, I will be using a dataset which contains 200 observations, 100 variables.
Recording in progress.
200 observations with 11 variables from a high school survey conducted by the National Center for Education Statistics in the USA. And we are going to use we are going to use the outcome or independent variable as the program type. This is basically one of the variables found or collected in the survey, and it's denoted as a prog. And then we are going to use the predictor variables, which is the socioeconomic status, which is categorical variables with 3 levels, and then also the writing score by the student, which is a continuous variable. The first step is basically to load the data. It's online, so we are going to run this line of code, and then we are able to load it into our R. And then we will perform exploratory
Recording stopped.
statistics. And basically, we want to view what the data looks like. And when we use view, it brings up the data in form of a table, as you can see. These are some of the variables you can see loaded on the screen. And then now we can actually get to see a brief summary of it through running the head code, right? And basically down here, you're able to see a brief of what the data is about. Further, we can
Recording
do
in
summary,
progress.
and here you can get a summary, descriptive statistics of what the data is all about. You can basically see the mean, the median of this data. The first process of doing the regression analysis is basically to convert one of the predictor variables, which is the program, to a factor. And this is what's happening on line 37. And when we run this, we are able to do that. That basically converts a prog, which is one of the variables, to a factor, and then set it as a reference level. Basically, what's happening here is that R needs categorical variables to be explicitly declared as factors for modeling functions. If you looked at the data, the original prog variable contains program types, which are academic. Here, if you can see prog here, we have academic, vocation, and then general. So this is basically why we need to do this line, because R needs them to be explicitly declared as factors for modeling functions. And then now the second part of this code, basically what it does is sets the reference level, which is the baseline category for the factor academic. And then we now need to set the second predictor variable to factor, which is socioeconomic status. And basically, this is what's happening on line 58. And when we run this, that happens, as you can see down here. So one of the predictor variable socioeconomic status, basically, it has three levels. We have low socioeconomic status, we have middle socioeconomic status, and then the high socioeconomic status. To perform the logistic regression, or rather the multinomial logistic regression, we basically run this code whereby we write the function multinom, and then we put pro, which is the dependent variable, and then the other independent variables in this format. Yeah, so what we see here is that sorry, are you able to still hear me?
Yes, we can hear you, Joseph.
Okay, thank you. What we can hear, or rather what we can see down here is that we get some summary statistics down here, whereby we are able to see what the model does. Basically, the model here, it estimates the log odds of choosing each of the non-reference category in the general or vocational versus the reference categories, or rather versus the reference category, which is the academic variable. Once we've run these, basically we are running the model. And then now we want to see the result of the model down here by basically running this summary model. And what we get from this, as you can see, we have the coefficients down here, the ones that I highlighted. And the explanation here we have, which basically what the coefficients are doing is that the coefficients represents the log odds of being in the general or vocation compared to the academic, which whereby we can interpret as that for 1 unit change in the predictor, we are able to see the results as seen below. For example, we can see for general versus academic, the socioeconomic status, or rather the middle socioeconomic status category has 0.533. When you compare this to the low socioeconomic status, the middle socioeconomic status decreases the log odds of choosing general over academic by 0.533, as can be seen here. And if you come to the says middle, which is the high, rather the middle socioeconomic class, we can see compared it to the low socioeconomic class, the middle socioeconomic status decreases the log odds of choosing general over academic by 0.533, as we saw before. When we come to the socioeconomic status, which is high, we have a figure of negative 1 point, which means that the high socioeconomic status decreases the log odds of the general versus academic by 0.058. Or also, you can see for vocational versus academic, the socioeconomic status, which the socioeconomic status for the middle class gives us a figure of 0.291. And this basically means that the high socioeconomic status decreases the log odds by 1.163 versus the low socioeconomic status. Basically, this is what you are seeing here. What we get from here, rather what from this model, is that the high socioeconomic status students are less likely to choose a general course or a vocational course or an academic course when you compare them to the lower socioeconomic status students. And then you can see the middle socioeconomic status class or a category of students, or students who come from such a financial background. They have mixed effects, whereby you can have negative, rather they cannot choose general courses, or they can choose courses in the vocation group. And then when we compare the writing score as a predictor variable, we get to see that higher scores in the writing score option, or other variable, reduces the odds of both general and vocation courses being chosen, with a stronger effect for vocation. I'll be sharing this code so that you'll be able to run it on your machines and be able to follow well what I've written or explained in the code. The next process, we can get the p-value using the Fed scores, or rather the Fed statistics. And basically, why we are doing this is to determine if the predictors have any meaningful, or rather, if they are statistically meaningful. For this, we interpret it in the sense that if we look at the critical values, if the p is below 0.05, the significant, that's meaning that the significant level is at 5% level. And also we check if p is below 0.01 to show a strong evidence against the null hypothesis. So what we are getting here is that the right score, or rather the score in the right variable, is significant for both general whereby we have 0.007, and vocation, whereby we have a P-score of 0.001. The socioeconomic status, high, meaning the people from the high socioeconomic status. The variable there is significant for the general courses, whereby we have a P of 0.024, but it's not significant for vocation, whereby we have a p-value of 0.099. Another test you can do is basically we calculate the predicted probabilities. And when we run this code, you can see the results down here, what we are getting. It basically assists us to show that the probability of choosing academic, which is the reference category, and also it assists us in seeing the probability of choosing the general and also the vocation. What we find, or what we can interpret from the result is that observation 1, basically this one, it has a 70% chance of being in academic, and then 20% in general, and also 10% in vocation. And then observation 2 is more evenly spread. Up to that level, I'll hand over to my colleague to continue with the visualization section. To be able to visualize the entire results on a graph, so that we can be able to better understand the relationship between the predictor values and the dependent values. Over to you, Steven.
Thank you, Joseph, for the wonderful presentation. Stephen, are you able to hear us?
Yes, I can hear you.
Okay.
I thought Kevin was to do something on visualization before I proceed. Is it not so, Joseph?
Yeah. So
Stephen?
I handed it over back to you to invite Steven, or rather to invite Kevin to proceed. I'm not sure if he's still around with us. Kevin,
Let's proceed. Let's proceed with the ordinal logistic regression. Stephen?
Okay, I'll share my screen. Let me share my screen. Are you able to see my screen?
Yes.
Okay. I'll do a presentation on the ordinal regression, ordinal logistic regression. And we used some data which is hosted online. This is the link to get that data. So what I did, I had to read the data from where it is. And then these are the first few lines of that data. And then maybe if you want to know the number of observations that we have, we can use the STR function. So we have 400 observations. For this data, we were trying to find out if the dependent variable was how to determine if a student will apply to undergraduate school. So our dependent variable was to apply, and the factors that were to determine if a student will apply to a graduate school or not apply was either if the parent was a graduate or not a graduate. And then the other factor that was to determine if a student was to apply to a graduate school was either, just a minute, whether he went to a public school or a private school. And the last factor was the GPA, which was the student's grade point average. So we had 400 observation and 4 variables for this data. Here, the dependent variable was apply, and it had 3 levels. The first level was unlikely, somewhat likely, and very likely. We had a total of 400 observations. So 220 students were unlikely to apply for were likely to apply to the graduate school. 140 students were somewhat unlikely, and 40 of the students were very likely to apply to the graduate school. So for the first variable, the first variable, which was the parent, if the parent was a graduate or not, it will determine if a student will apply to the graduate school. From this data, we found out that 337 parents were not graduate, and only 63 of them were graduate. And then from the same data, we found out that 343 students went to a public school, and only 57 of them went to a private school. In line 27, we are going to have a 3-way cross table. This shows the combination of the kind of school that the student went, and if the parent was a graduate or not a graduate. So for the 175 students, they are unlikely to apply for the graduate school. And then if we go to this last line, the very likely, we will find out that 7 of them were from a private school, and then their parents were not graduate, and 3 of them were from a private school, and their parents were graduates. And here is a summary of the GPA points. The minimum GPA point was 1.9. The first quartile was 2.72. The median was 2.99. The mean was 2.999. The third quartile was 3.27. And the maximum GPA was 4. We had a standard deviation of 0.3979. And then here we use the ggplot to have a graphical presentation of the data. So on our y-axis, we have the GPA, and on our x-axis, we have the apply. If the student is unlikely, somewhat unlikely, or very likely to apply. And this was the visual representation of our data. So we went ahead and fit the ordered logit model. We had to use the mass package. So we installed it, and then we called it using this library, mass, and we plot the ordinal logistic regression. Our dependent variable was apply, and then this was the independent variable which represented the parent, if they were graduate or not. And this was if the student went to a public school or a private school. And lastly, these were the GPA, the grade point average. And then we view the summary of our plot. This was the output that was generated. We have the values, the standard error, and the t-value. And then here we have a summary of the coefficients. And then here we use the p-norm to have this output. The value, the standard error, the t-value, and the p-value. This line was to give the confidence interval, and here we have it. And we calculated the odds ratio using this exponential and then the coefficient. We found out the exponential of the coefficient to get the odds ratio. And from the odds ratio, it's where we can have an interpretation, our final interpretation. Here we just combine the odds ratio and the confidence interval. And then here it's the interpretation using the odds ratio. From the odds ratio, for the parent, we had a value of 2.85. For public, we had a value of 0.9429. And for GPA, we had a value of 1.8513. So if we'll have to do an interpretation of that, under the parental education, we had a value of 2.85. So the interpretation is that for students whose parents did attend college, the odds of being more likely, i.e. very or somewhat likely versus unlikely to apply is 2.85 times that of student whose parent did not go to college, holding constant all other variables. And then for students whose parents did not attend college, the odds of being less likely to apply, meaning that unlikely versus somewhat or very likely, is 2.85 times that of students whose parents did go to college, holding every other variable constant. For school type, for students in public school, the odds of being more likely, into bracket, very or somewhat likely versus unlikely, to apply is 5.71% lower. That's the difference between, because it was less than 1. Here we had 0.94. So we had to subtract this value from 1. That's what's happening here. Than private school student holding constant all other variables.
David, maybe you can speed up because time is really running out.
Okay.
Okay.
For GPA, for every 1 unit increase in students' GPA, the odds of being more likely to apply is multiplied 1.85 times, holding other variable constant. For every 1 unit decrease in students' GPA, the odds of being less likely to apply is multiplied by 1.85 times, holding constant all other variables. Thank you. Back to you, Abigail.
Thank you, Stephen, for the very extensive presentation. Is Calvin still presenting?
No, we are done. Huh?
Okay, so thank you very much. We can appreciate them. They have done a good job. Any questions from the class?
Maybe I can go first.
Yes, please.
Maybe to the team. What are the link functions that are used in ordinal logistic and multinomial, or other nominal logistic? Then number 2, in a nutshell, when do you use ordinal logistic and when do you use multinomial? Over. Sorry, did you hear me?
Directed to the group members. So please, we can save on time and you can shoot your answers.
Okay, let me go first. The link function for ordinal logistic regression, it's logit. That's the default and most common used link function. But we have other ones like probit, cloglog, and couchit. Thank you.
And the second question on when do you use multinomial and when do you use ordinal logistic, in a nutshell? When you have what kind of response variable?
So for multinomial logistic, Calvin, you can go.
Okay, so you use multinomial logistic regression when you have the response variable having categories that are not ordered or they are not having any natural order. Whereas in the ordinal logistic regression, use it when the response variable has categories that are ordered in nature, and there must be more than 2 categories.
I think that's all from my side. I think it was a good presentation. I also like that you used LaTeX to be able to make your presentation, which I would encourage all of you to try and learn ahead of writing your thesis when the time comes. Thank you for the presentation. Other colleagues can ask questions if there are any.
Any questions from the rest of the classmates? If there's none, we can appreciate them. invite the third group to do their presentation.
Good evening. I hope you can hear me.
Yes, William, good evening. We can hear you.
Great. So this is group 3, and we are tasked to see or to discuss Poisson regression and log linear models and its applications. So in this group, we were 7. So these are the names of the group members. Then I'm going to have kind of a lecture, but I'll try to be as brief as I can due to time. Just 1 minute. Let me try to remove this. So this is a gentle introduction to Poisson regression. I'll be presenting Poisson regression. Then the other members will come in to present log linear. So as we know, this is a type of generalized linear model used for modeling where the response variable consists of count data, and that count data should always be non-negative integer. And the response variable follows Poisson distribution. So when we talk of Poisson distribution, it means like mean and variance should always be equal. So for it to be termed as Poisson distribution. So Poisson distribution, I'll just try to explain, describe the probability of a given number of an event occurring in a fixed interval or time or space. So as much as we say it's a count data, in most cases, this is applicable where we have rates. Like for example, you want to see maybe how many offers are being received per 1,000 people, maybe in a year or a month. So there is an element of rate and period involved. So basically here we are looking at the probability mass function, whereby like we look at the, we have the base of the natural logarithm, which is an E or Euler number raised to lambda multiplied by lambda raised to y divided by the y factorial. So in this case, y means the number of observations you are having. So it can be yi, maybe to yn, depending on the situation. And then you can go through this. So basically it's all about explaining what is going on there. And then I have down here the properties of the what we have to look when we are looking at the property. As I said, mean and variance should be equal, which is normally called equidispersion. And then if variance is greater than the mean, then Poisson regression normally underestimate uncertainty, and we can explore other models, which we are going to look into as we go on. Now, this is kind of like how the model looks. This is the architecture of the model. So when you look here, we have log into what we call lambda. Now, I just want to give an overview of this. So log is a link function, and then betas, like just 1 minute, beta 1, beta 2, up to beta k. These are linear predictors, and then basically the model follows Poisson distribution, as we already discussed. The mean and the variance are equal. Now, when we look at this, we are normally looking at the log odds, which is very, very hard to interpret. So what do we do for us to have a better interpretation? And that's why exponential form comes in, whereby you are going to get all the predictors. What you get, you have the natural log raised to the predictor to get what we call IRR. So we're going to see what exactly is IRR as we go on. So Poisson regression follows a couple of assumptions. First, response variable consists of count data. So which should be, it includes integer 0 or greater and cannot be negative. Observations are independent. Each observation in the data set should not be related to another. And then a log linear relationship, that's like predictors should have this kind of relationship. And then a distribution just follow the Poisson distribution, which we normally call equidispersion, where variance are equal to mean. Now, when you look at the fourth assumption, in most cases, is always violated. This is a case where we have overdispersion, and this is most commonly in when we are handling such kind of problems. So how do we check this, like we are fulfilling these assumptions? First of all, we can go ahead and check Poisson chi-square test to check for overdispersion, and then residual analysis, where we can also go ahead just to see that what we are going on, because the residuals will always be random when you are looking at or you are plotting the residuals. Now, how do we get like maybe the coefficients, or how are the coefficients estimated? We normally use what we call maximum likelihood estimation. And this is the formula. Maybe you can go ahead and just check how it works. And then we normally take the log likelihood for optimization. And this is just like manipulating the formula we had before. And since the model is log linear, so this we are talking about how do we interpret. For instance, if you are interpreting based on the coefficients you get, that means like, for example, a 1 unit increase, for example, this is a xj, the expected log count changes by bj. Bj is just the looking at maybe we have age and so on and so forth. And then we go ahead and look at the incidence rate ratio. This is where we get the base of natural logarithm raised to what we got from the coefficients. We should be able to get a better result whereby we can be able to interpret it. So this is like just multiplicative effect on expected count. For example, if I have this kind of like my beta, like for example, I say beta 1, which is like maybe division, it is 0.2. So if I want to get the incidence rate, I just take this and then I get the base natural logarithm raised to this power. Then whichever I get, I'm going to get like maybe 1.22. So this means like there is 22% increase in expected count. So, and maybe we can just check a case where we have overdispersion case. If the variable is greater than the mean, how do we do that? So instead of just using Poisson regression, we can go ahead and use what we call quasi-Poisson regression or negative binomial regression. So quasi is just to adjust standard error for overdispersion, and negative binomial is just to add some extra diversion parameter. So let us see how the application. One is just like it can be used in call center, whereby like you look at the number of calls received by a call center per hour. Remember I said mostly you are looking at the rates. Then you can also look at like the number of customers arriving at the store per hour. Maybe even you can just go ahead and check, like if you want to know the typos found per page in a book, as well as others, I think you can just go ahead and check. There is a lot of applications, but this is just a few. So on this note, I'll go directly to the code, which I'm going to show you. I try to use a simple way so that at least people can understand exactly. Now, look at it. You are a data scientist and you are approached by Kenyan Football Federation, and they just want to know how many scholarship offers a Kenyan football player can receive based on either the current team division, which we just decided to have ABC. So normally we have like those like in counties and so on and so forth. And then also based on exam score. So normally they have trials before even they join maybe the national team, or maybe they want to go and play outside the Kenya. So we have some exams like you are called just to see your skills, and then they record the exams. Can we be able to have this kind of situation and then predict the kind of offers this footballer can be able to have or to receive? Now, this is a data set that was created. So I have offers, division, and exam. If you look closely at the offer,
Excuse me, William.
Yes?
Sorry for
You're not
interrupting.
sharing. Sorry.
Yeah, we cannot see. Which screen are you sharing? Is it the presentation one?
Am I presenting the codes?
The slide.
Maybe stop
Oh,
sharing,
sorry.
then share again. Yeah.
Let me stop and then reshare. Sorry for that.
Okay.
Just a minute. Just confirm if you can see my R Studio.
Yes, we can now see it.
Great, thank you. So I'll just start again. So I said, suppose we want to know how many scholarships offers a Kenyan footballer player receive based on their team division and their trial exam score. So exam score is measured from 0 to 100. And here I just created a data set. So offers, I wanted like 50 players didn't receive an offer. One player, a 30 players, sorry, received one offer. 10 players received 2 offers. 7 players received 3, and 3 players received 4 offers. And then in division, we have a sample ABC. So we have 100 samples based on this number. And then exams, how they scored. So we have 50 players received between 60 and 80 marks. 30 players received 60 to 95, and then 20 players received between 75 and 95. So this round is just to at least make my 2 decimal points. So you can attach data if you don't want to be using every time you call the data frame and then the variable. So I attached my data, and then normally we have to understand our data, how it looks. So that's why we have head, structure, dimension, and the summary. So this is how my data set looks like. So this is just like first 6 rows. So we have exams, offer, division. And then when we come here, this is where we have like 100 observations and 3 variables, columns. And then if we look at the observations or offers, so we have like the minimum is 0, meaning we have guys who didn't receive any offer, and the maximum we have 4, so meaning some even received 4. If we look at the exams, the minimum was 60.7 and the maximum was 94.25. That's exams. Now, are we able to see what kind of, or between these 2 variables, which one is more significant, statistically significant? We are going to see as we proceed. So this one is just to see like offer, mean, normally like because we need to do some kind of statistical, concise statistical before we proceed. And then here we also see based on these guys from division A, how many people received the offer? And I think this is just like how many players came from division A, how many came from division B, and how many came from division 3. If you add this, it's 100. Now, as we said, sometimes we need also to look at the assumptions of Poisson. So that's why we went ahead and checked for histogram. And it's quite interesting here to see, like, most of the players received either 0 or 1. Looking at this, most of them received 0 and 1. And this typically for data which follows Poisson distribution. So a decent chunk of responses have values 0. This is why we have that kind of visualization. Now, let us try now to fit our model and see how it works. So we use GLM function, and our response variable is offers, and predictors are division and exam. Remember, division is categorical. That's why we are using factor. And then family basically is Poisson family. And then we go ahead and do just summary to see what's going on. So this is quite interesting. If you look at these values here, you look at the coefficients. So you can see we have like exam is very high and is statistically significant because the p-value is less than 0.5. But now, when we look at such kind of like division, like maybe B and so on and so forth, based on or equating it on the base value, so you can see like we have a very somehow big, but now when you look at this, they're not statistically significant because the p-values is more way bigger compared to the alpha value. Now, here's the issue, like, so the coefficient of exam is 0.086, which indicates the expected log count for a number of offers for a 1 unit increase in exam is 0.84. So do you think this can be like, if you maybe tell someone who doesn't have idea in tech can understand? No. And that's why we have to go for instance ratio rate. So we are getting, like we already saw in the slides, we are just getting the value here. We get our natural base of natural logarithm, and then we get raised to this power. And this is exactly what this code do. And now if we look at this code here, this is what we have. Now this means we can be able to interpret it in an easier way. I just gave an example of exams. So it means there is an 8% increase in the number of offer for each additional point scored in trial exams. So this, you can do the same with this. Unfortunately, I didn't get maybe 0, maybe based on this, which is very small, which is okay, because we are looking at these other factors constant. But now if it's a 0, it means like it will be a decrease in the number of offers as we have like maybe for each additional point, if it's like maybe less than 1. Now, we can also go ahead and see confidence interval. And this is at 95% confidence interval. So like in this case, if I look at the exams, a 1 unit increase in exam score, the risk of outcome multiplies by a factor between this one and this one, which is 1.064 and 1.117. This is how you interpret the confidence interval. Now, remember, this is kind of like more of categorical. We can go ahead and just check the chi-square test just to see how best we can get something from there. So if you look at this value here, this one. So we can get chi-square from residual deviance, and we have 82.73, and then degree of freedom at 96. So we can feed in here. So Q just observed chi-square test statistics. So basically chi-square is just x squared, and then degree of freedom at 96. So if we run this, we are getting at 0.30. What does it mean? So it means like, because this is p value of chi-square, it's more higher compared to alpha value. So when you look at this, it's not statistically significant. But again, we can say maybe the observation or the data we have can help us at least to come up with something, even though it's not statistically significant. Then we can also go ahead and just come up with a visual to see how our model is predicting what we are trying to find out. Now, when you look at this, I just used ggplot, and then we are looking at the response, and then we are looking at maybe division, and then exams. So if you look at this is what is giving us. What do you think is trying to help us understand? In this case, we can see blue, it's from division C. And then if you look also closely, these blues are bigger. So how do we interpret this? So the expected higher scholarship offer goes to those who score higher in the trial exams. And those players in Division C gets more scholarships. So that's exactly what this is trying to predict. However, we need also to look into it here. As much as we are looking at the division, but they're not statistically significant. So it means in most cases, the offers will be determined by the exam score. And that comes to the end of the first presentation. Okay, so I'll invite Olo, I think, to proceed to the second presentation about log linear model. None from group 3 to proceed, please.
Thank you, William. Olo, are you here with us? If you can hear us, please proceed. Brian. Yeah.
Yes, hello.
Yeah, please proceed.
Can you hear me?
Yes, we can.
Yes, I'll take you through the log linear models.
Okay.
And let me pass share my screen. I hope you can see my screen.
Yes.
Oops.
I have a problem with my laptop, so maybe it is hanging.
Let me project from my end then.
Okay.
Okay, you can stop sharing.
Okay, so we'll talk about the log linear model, and as models are just type of generalized linear models which is used for analyzing categorical data where the relationship between variables is multiplicative. They model the logarithm of expected cell frequencies in contingency table. A contingency table is a type of table used in statistics to display the frequency distribution of two or more categorical variables. For example, in this data, we have the rows and columns, and our rows contains entries of smokers and non-smokers, and the columns contains the entries of conditions if yes and the condition 2 if no. So the values inside here, for example, 15 shows that a person is a smoker, and the condition is yes. It gives us account data of 15, and then the next one here is 25, where a person is a smoker and the condition is no. It gives us account data of 25, and the row total for the first row is 40. The second row is where we have the non-smokers. When the person is a non-smoker and the condition is yes, we have a value there 5, and the next one is 55, and the total is 60. So in this case, you will realize that log linear models assumed a Poisson distribution for cell counts. These values 15, 25 are the cell counts, and it is used for multi-way contingency tables, e.g. 2 by 2. For example, this contingency table is a 2 by 2 or high dimension. It is an extension of chi-square. It is an extension of chi-square test for independence, but allows for more complex relationship. Okay, we can proceed. Okay, we have when to use the log linear models. Log linear models is used when analyzing association between categorical variables. Here, we use log linear models when you want to study the relationship among two categorical variables, e.g., gender and smoking status, for example. Also, you can use log linear models when testing independence. But it is similar to chi-square, but more complex, but more flexible. The third reason when to use the log linear models is when modeling interaction between multiple categorical variables. And then we have the model structure. The model structure contains a link function that is log u, its ijk, which is mapped to the sum of the independent variables here containing the parameter lambda. And here you will realize that the first lambda is a constant, which shows us the overall mean. And the second lambda contains the power of a, which shows us the main effects. Then we move to the one with the interaction that contains the power of AB, AC, and BC. And then lastly, the one with the three interactions. Okay, we can continue. So the applications of log linear models. Log linear models is used in social sciences. For example, you can use log linear models to explore the relationship between gender, education level, and political affiliations. That is in social sciences, social science setup. And also, you can use log linear model in biological setup to study the relationship among risk factors, disease presence, and geographical areas. And lastly, we can use log linear models in market research to evaluate how region, promotion type, and sales volume are related. So maybe the next person can continue with the code part.
Who is supposed to take us through that? Brian? Hello, can you hear me? Brian or William?
Abigail, we can hear you. But, Brian and William, who is doing the next part on the codes for log linear?
I think it was Kevin or Peter. But if they're not there, then maybe I can just walk you through first.
Let's proceed.
Yeah, thank you. So I'll be a bit brief. So in this case, as we have seen, log linear model is basically purely used when we are trying to do prediction on categorical variables or categorical dependent, not independent variables. So in this case, we are trying to see whether UCBA admission dataset can give us a better way to handle this model. So UCBA admission dataset is an inbuilt dataset in R that document graduate school admission decisions at the University of California. This was normally in 1973. It's an old data, which is basically purely used on these log linear models. And it's a classical example of statistics. We use it to analyze association in categorical data using log linear models. So We loaded the data, the same thing we did, like just checking the head, how the data looks like. So you can see here we have admission, which is the main prediction, whether someone will be predicted or not, or will be admitted or not, based on gender, department, and frequency. Then admission, we have to either admitted or rejected. Gender, we have male and female. Department, we have A to F, representing 6 departments. And then we have frequency, which is just a cell count. So key types of linear, log linear models, we have a couple of key types. So we have saturated model, which looks at all possible interaction included. And you can see here, we normally use multiplication sign to link the independent variables. And then we have the model which there is no interaction, which looks just like Poisson or any other models that we normally do. We don't have any interaction. And then we have partial association. So meaning we can have some independent variables not linked, and some are linked to one another. Like for example, here we have A and B and A and C. So if you look at this code, we did 3 models at a go. So we have one with all interaction by using this, and our dependent variable is frequency. And then we also no interaction. So this one here is just using a plus. And then here we have partial interaction where gender and admission is linked together. And the same family is Poisson. So sometimes you can also use log GLM to do the same. It will give you the same result. Now, as we did previously, we also need to look at the likelihood ratio test, whereby it's going to give us a better view and how to interpret the result. Then after that, we can also look at the partial chi-square, whereby we are just going to look at, do we have any relationship among the variables? And then we can look at the difference. This is where we have this variables, and normally lower value indicates better fit. So in this case, if you look at this, we have like 3 models. So you can go ahead and check out of the 3 models, which one is giving you the lower value. So the lower it is, the better the model. And since the model in log linear coefficients represent multiplicative effect on expected counts, converting coefficients to RR. So this is a risk ratio, which is similar to incidence risk ratio, the one we saw earlier, for interpretation. So we have to change everything into RR. And this is exactly what we are doing, the same exponential, then coefficients, and then we just put the model. Then this one will also give us the same information when you are interpreting. Like for example, if we say beta 1, which is 0.68, this one, gender female. Now remember, this was, I think this I also wanted to ask the question. Here I tried without, we did put anything like factor, but surprisingly, it gave us the same result, like even if you're using factor. And if you are keen, you'll see like, it doesn't, like if it's 3 subcategory, it will give you 2, and then maybe the one which is base, it will not show. So this is exactly why we have gender female, we don't have male.
Maybe for that, William, you'll do STR into bracket, then the data set.
Okay.
Just in case I forget. So you'll do STR into bracket data set, then I'll answer that question that you've asked later on.
Okay, thank you. Okay, so this is what we have here. Like for example, if we have gender female 0.68, What does it mean? So remember I said if it is 0, it's not 1, then there is a kind like you have to look at what is lacking here to make it 1. So observation beta 1 0.68, female have 32 lower risk of being selected compared to baseline male. So we are looking at the baseline because this is categorical variable. But if it was just this one, then we are just looking at it. Risk will be less and so on and so forth. So this one, there is an increase by 57%. So checking the best model for full interaction model. So this one, like we are looking at the full interaction, meaning model 1, which we are just using the multiplication to get it. And then you can see we have very many here. Unfortunately, here we didn't get due to time, we didn't, I was unable to check out exactly among this, like if you look at this, we have very many models here. So which one is the best among these? You can see when you look at this result, we are having the first model. Remember, when we are talking about if you want to know how many models you have, it's 2 raised to power n. So the number of variables. So this is what is happening. So we have very many models, but here you cannot be specific, like which one is the best, but this is how you go about it. Then we also have like visualization log linear models, which we did, but unfortunately, I can't tell exactly how to interpret this. But this is what it says, like shaded cells, red is overestimated, blue is underestimated. So when you look at this, we have admission versus gender. And then here we have department. And then this is just an overview of what we did. So linear log summary is used for categorical data in contingents table. 2, when you're looking at the model structure, this is how it looks like. So the link function is log still. And then we have the main effect plus interactions. And then to test the fit, we use LTR, Poisson chi-square. And then to visualize, which is this one, we use mosaic plot from VCD package. And then always watch for over-dispersion, whereby if there is over-dispersion, always go for quasi-Poisson if needed. And then you just change the model. Instead of Poisson, you use quasi-Poisson. Otherwise, I know this one we didn't do it well in terms of interpretation, but that was our effort from group 3. Back to you, Abigail.
Thank you very much, William. Together with your group members, we can appreciate them. And the floor is open to questions. Prof, maybe you can start.
Sorry, William.
Yes.
Maybe the question that you had asked, maybe you can do STR for that particular data set.
Yeah, I think I did it here. So let me
Where's the
check.
result?
Just 1 minute. I think it's here. No, it should be here. Yeah, it's here.
So if you look at STR, if you look at admin,
yes,
it's already converted to a factor.
Oh.
So it's already defined as a factor. But remember, if you read it and you don't define it, it will be treated as a numeric. And if it is treated as a numeric, then it's your duty now to convert it to a factor used by introducing that function factor inside your model. But if it is already converted into a factor inside your data, then you don't need to write factor in your model. I don't know whether it's making sense.
Yeah, it's making sense.
So it's already converted to a factor inside the data itself. So you don't need to redo it again. But I will always urge you when writing your codes, always just put the factor again, just in case somebody didn't convert it before, then you catch it in your model.
Okay.
Okay.
Yeah, thank you.
I saw your response variable was was it frequency or what?
Yeah, frequency.
I need to see the head of the data, how the data looks like, especially looking at the frequency bit. Oh, okay. So it shows those who are admitted and are male and belong to Department A are 512. Is that the interpretation of the table?
Yes.
Okay. Okay. Okay, so these are the counts for those combinations, right?
Yes.
Okay, now I think that's clear. Okay. I think this is fine.
Thank you.
Yeah. And I think it's clear for me. Abigail, back to you.
Thank you. Any other questions for the group from the class, if there is? You guys don't ask questions? Anyways, okay, we can appreciate all the groups for the effort they made and for putting the presentations together and working together to make this a success. I think that's all from my side. Over to you, Prof.
Thank you. I'll be sharing the codes later.
Oh yeah. We can share the codes via our platform for all the groups and together with the presentation slides. Yeah, thank you.
Thank you, Abigail. No, and also appreciate if you can have the codes and the presentations for all the groups. Now, I think, guys, I'm proud of you. You did a very good job. You went and did your homework and were able to deliver what I expected and even surpassed what I actually anticipated to see. So I think it's a very good job from your side. And it shows the amount of time that you invested in this. I'm happy for those who are already using LaTeX. For those who are not using LaTeX, please learn from the other guys and try and learn how to use LaTeX and to make presentations using LaTeX. In terms of understanding, I think I've seen a high level of understanding from all the groups, and all the things that you presented were factual. And I like the way you knitted them nicely with the data and the applications. I liked what William's team did, where they were able to even randomly generate data. And in one instance, they used internal R data. I think that was also very innovative from their side. Now, I think I'm happy. I'm happy with the presentation. That's all I can say. Any comment from anybody as we close? Comment, question from anybody? Okay. Now I think we stop. Okay, shoot.
There was a story that you were telling us some time back. I think the time when you were in Djibouti, and then
Okay.
the mate did the thing.
I know there was a story. I'll try and remember the whole story. Then I'll give it before we finish this unit.
Okay.
It was about
What
the
was it
Python
about?
guy. The
It
Python
was
guy.
about Python. Yes, Python. Yes.
Whom you are showing some things. Yeah.
I'll try and figure it fully. Then I'll be able to share it with you. Is that fair enough?
Sure.
Okay. Thank you for the reminder, and thank you guys, and have a good evening. Bye-bye.
Recording stopped.
Bye.
Okay.